So now we will do another question on the construction of Bode plot. Sketch the Bode plot of the unity loop feedback system whose open loop frequency function is given like this. So now we will see how to construct the Bode plot. Now you can see that this is already in the time constant form and it is already in the frequency function, right? We've already expressed in terms of frequency function. Now what is it that you have to identify next is the corner frequencies. So what will be the corner frequencies? There are only corner frequencies corresponding to poles. Okay. So one will be at 1 by 0.1 and another will be at 1 by 0.05. That means 10 and 20. These are the corner frequencies corresponding to the poles. Right. Next we will see what will be the initial slope and initial value. First, if you see the initial slope, there is one pole at origin, right? So what will be the initial slope? It is going to be minus 20 dB per decade. And what about the initial value? It will depend on the frequency that we are taking. Let us take, let initial frequency be omega is equal to 0.1. Then what will be the magnitude at omega is equal to 0.1? This will only correspond to the gain and the pole at origin. So 20 log k, which is nothing but k is given as 10 here, minus 20 log omega. Okay. So this will give you omega, if you substitute 0.1, it will give you 40 dB. Okay. From this information, you can get the magnitude plot, right? So first you draw the axis. This is the frequency and this is the magnitude. Okay. Now where will the initial value of frequency we have taken to be 0.1? So for this the magnitude is going to be 40 dB and here it will fall down at a rate of minus 20 dB per decade. Okay. Now let us say omega is equal to 10 is here and omega is equal to 20 is here. At each of these corner frequencies there will be a change of minus 20 dB per decade. Why? Because here the corner frequency is corresponding to the poles. Okay. So that is why change will be minus 20 dB per decade. So here there will be a change, here there will be a change. So till that frequency is reached, the slope will be minus 20 dB per decade. Here the slope will start falling at minus 40 dB per decade and at 20 it will further fall at minus 60 dB per decade. Okay. Another information that you can show is when will this magnitude become 0 dB. Okay. So let us assume that the 0 dB is achieved in between these frequencies. Then what will be the expression for magnitude? It is going to be 20 log k minus 20 log omega. So this, if it has to be 0, then what will be the value of omega, right? So here omega will be equal to k, which is 10. Okay. So that means here itself it is reaching 0 dB. So you can either mark 0 dB here, or if you want the axis to be having 0 dB, then you can simply redraw. This is the magnitude. Here you have omega is equal to 0.1 and the magnitude is 0 dB here. Then how will you draw? The plot will start at 40 dB. Let us say this is omega is equal to 10 and this is omega is equal to 20. Then initially it will fall at minus 20 dB per decade and at omega is equal to 10 the change will be minus 40 dB per decade. And once again at omega is equal to 20, the slope will further change to minus 60 dB per decade. Okay. Next is the phase plot. So phase plot, you can either draw individual functions or you can directly get from the expression for the phase. What is angle G? This is going to be minus 90 degrees because of the pole at origin minus tan inverse 0.1 omega minus tan inverse 0.05 omega. Now when omega is equal to 0, then angle G is simply minus 90 degrees. When omega is tending to infinity, then angle G is equal to minus 270 degrees. And you can see that as omega increases, angle G magnitude will increase but in negative sense. So that means it will become minus 90 to minus 95, minus 100 and so on to minus 180 to minus 270. Okay, so this is how the phase is going to increase. So since this is very direct, you don't have to use the individual plots. So how you can draw this? This is angle G and this is the frequency. You can take an initial value of omega is equal to 0.1 or 0.01. It should be close to 0. Okay, so let us take 0.1. Then it is starting at minus 90 and then it is going to keep falling till it reaches how much? Minus 270 degrees. Next question is find transfer function corresponding to the following Bode plot. So this is the Bode plot given. So till now we have only plotted the Bode function, right? Now from the given Bode plot we have to find out the transfer function. So we've already discussed a few points as to how to do this. So now let us apply to this problem. So the very first thing that you should notice here is what will be the initial value and initial slope. These both will give you information about the constant and the zeros or poles at origin, right? So initial value and slope. So the slope is falling at, it is a negative slope, minus. So that means there will be a pole at origin. How many poles at origin? Usually we write as minus 20 n dB per decade for n number of poles. Alright. So now it is minus 40 dB. So if you equate minus 20 n to minus 40, you are going to get n is equal to 2 poles at origin. So we have found out how many poles are there at origin. Now we can find out the initial value. So when there are 2 number of poles at origin, what will be the expression for magnitude? 20 log k minus 20 n log omega. This will be the magnitude, right? And this is given as 80 dB. This is when omega is 0.1 and n also we know it is 2. So 20 log k minus 40 log 0.1 is equal to 80. Log 0.1 is minus 1. So this will become plus 40. So then what will you get? 20 log k is equal to 40. This is going to give you k is equal to 100. Okay, so we got the constant as well as the number of poles at origin. Next what we can find out? We can find out the corner frequencies. Wherever there is a change in slope, there is going to be a corner frequency, right? So you can see that there is a change of slope at 2, 5 and 25. But what is the change in slope? At 2, the slope is changing by minus 20. From minus 40 to minus 60 it is becoming. So this will correspond to one single pole. And what about at 5? It is changing from minus 60 to minus 40. That means slope is increasing now, right? It is becoming minus 40. So the change is plus 20 dB per decade. So this will correspond to a 0. Similarly at 25, it is becoming from minus 40 to minus 60. So this will correspond to a pole. So first you can write down the corner frequencies. This is going to be 2, 5 and 25. At omega is equal to 2, change in slope is from minus 40 dB per decade to minus 60 dB per decade. That means change in slope is minus 20 dB per decade. So this is going to be a pole of order 1. Okay. And at omega is equal to 5, the change in slope is going to be from minus 60 to minus 40. So that is change is plus 20 dB per decade. So this is going to be a 0 of order 1. Finally, at omega is equal to 25 with a similar analysis, you are going to get that there is a pole of order 1. So therefore, you can finally get the final transfer function. You have the constant as 100 and there is going to be a 0 at omega is equal to 5. So what will it be? 1 plus j omega by 5 divided by how many poles are there at origin? The order of poles at origin was 2. So j omega whole square into another pole and poles we have at omega is equal to 2 and 25. So you're going to get 1 plus j omega by 2 into 1 plus j omega by 25. Because when you write 1 plus j omega t, then what was the corner frequency? 1 by t. Okay. So if the pole is given at x, then it will become j omega by x. So now you can also further write in terms of s. Wherever there is j omega, you write s. So you're going to get 100 into 1 plus s by 5 divided by s square 1 plus s by 2 into 1 plus s by 25. This is the time constant form. You can also write in the pole 0 form. What will it be? You're going to get 100 divided by 5 into s plus 5 divided by s square into s plus 2 by 2 into s plus 25 by 25. So this is going to come out as 1000 into s plus 5 divided by s square into s plus 2 into s plus 25.